Welcome back to geometry. We are at 4.6, congruence in right triangles. Alright, the key word here is we're dealing with right triangles, and so in all sections previous to this one, from 4.2 to 4.5, we have been learning about side, side, side. We've learned about side, angle, side. We've learned angle, angle, side, and angle, side, angle. And so we learned that these four rules work when trying to prove that two triangles are congruent. Now, these rules work for all triangles, okay? And then there were two rules that didn't work for all triangles. That would be side, side, angle, and angle, angle, angle. These two did not work. What we're going to find out momentarily is that side, side, angle will actually work, or a form of it will work when dealing with right triangles. Now, keep in mind too that all of these four, side, 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 angle, side, angle, angle, side, and angle, side, angle, will also work in right triangles. So we're going to keep everything the same that we've already learned. We're just going to add one new one, and it's actually not called side, side, angle, because this spells a bad word, okay? It actually will be called the HL theorem, but you'll see that in a sense it's pretty similar to side, side, angle. Alright, we're going to start. It says if we bisect, and I believe that's going to say vertex. Yes, that says vertex. So if we bisect the vertex of an isosceles triangle, and that's a key word, then it will be the perpendicular bisector of the base. And we're being asked why. Well, first let's do that. So if we bisect the vertex, so let's put angle A, let's put angle B, we'll put angle C, and so if we bisect angle B or cut this angle in half, this line is going to come down, and it's going to create 90-degree angles here and here, and these two angles are the same. Now, I'm not going to show that, but know that since this angle is bisected, these two angles are the same. But for right now, I'm just going to hold off on that. Since the triangle we're told is isosceles, we know that these two sides are the same. Okay? And then by reflexive property, let's put point D down here. By reflexive property, I can put 2 marks on BD. It's shared on both sides. So as I look at this triangle, clearly I have side, side, angle, and side, side, angle. So as we look at these two triangles, remember we're trying to prove that this triangle in green is congruent to this triangle on the right. And so from the old ways of doing it in previous chapters, we would see that what is formed here is side, side, angle. And in the past, we would say, no, these triangles aren't congruent. Well, this is now incorrect, okay? And it's incorrect because we have a new theorem that says HL theorem. And it says if the hypotenuse and one leg of a right triangle are congruent to the hypotenuse and one leg of another right triangle, then the two triangles are each congruent. Now, let's think about what this is actually saying. It's saying if the hypotenuse, here's the hypotenuse right here with BC and AB, and remember the hypotenuse is always opposite your 90-degree angle, So clearly these hypotenuses are congruent to each other. And then a leg, your leg is going to be BD. So again, if we were to redraw this right triangle and we had a 90-degree box here, we could say this is a leg and this is a leg. So either one can be used as our leg, and this is always going to be our hypotenuse. So this is exactly what we have here, and so this is called the HL theorem, and we can now say that these two triangles are each congruent. All right, now why does the HL theorem work? Well, here's why. Remember that we were told at the beginning that this is an isosceles triangle. That means their sides are congruent and base angles are congruent. And that's the big one, because when I draw in these base angles, now you see angle, angle, side, and angle, angle, side. So you see why the HL theorem will work, because it has 90-degree angles. And so these two triangles are congruent by angle, angle, side. But for now, we can just stick to the HL theorem, which in a certain sense is similar to SSA. And why are these two shapes congruent? Because we actually created two congruent triangles. To use HL, which stands for hypotenuse-leg theorem, what needs to be true? Well, we need three things. We need to know that we have two right triangles. We need to know that we have two congruent hypotenuses. And we need to have two congruent legs. So as I look at these problems down below, it's saying mark the congruencies implied by what's given. So we're given BC is congruent equal to AD. We'll put a mark here. Also, let's by reflexive AC is congruent equal to AC. And so we're being asked, are these triangles each congruent or are they not? Well, these triangles are congruent. And at first you're saying, wait a minute, I can't use side-side angle. Well, remember, in a right triangle, the rules change. We now have what's called our HL theorem, which replaces SSA. So this is clearly a case. Here's our hypotenuse, hypotenuse, and leg, leg. So this is going to be yes. ABC would be, or if they go ABC, we would have to go ADC by HL theorem. C is the midpoint of AD. Please put marks here and here. By reflexive, this is BC is equal to itself. Triangle ABC is congruent equal to triangle DBC by side, angle, side. Now you might be thinking, wait a minute, how come we didn't use HL theorem? Well, remember that on right triangles, we have 5 choices. We can use side, 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 angle, side, side, angle, angle, side, and our new one, HL theorem. Okay, but we're not always going to use HL theorem to prove that right triangles are each congruent. We still have all these other 4 methods that work. So this is side, angle, side. Alright, this problem is very challenging. So the first thing we always should do is we should highlight which 2 lines are parallel. We're told AB, so let's highlight line AB and always extend it out. And CD. Okay, now keep in mind that whenever this happens and we're involving triangles, it's usually going to lead to alternate interior angles. That's what we have to focus on. We're being told that 2 lines are both parallel. Now, please note, we know nothing about line BC and line AD. Now, it appears that these lines are parallel, but without arrows, we can't assume it. So for right now, these lines aren't parallel because we're not shown arrows. Then always highlight your transversal between 2 parallel lines. That's this line right here. And what's interesting here is between this line that are both parallel and this line and this transversal, these are alternate interior angles, but they're already shown as being each congruent. So that doesn't help us in any way. One thing that will help us is that AC is congruent equal to AC by reflexive. But this is all that we know. So we have angle, side, nothing, angle, side, nothing. So this is not enough information. We're going to say not congruent. All right, problem 4. AB is congruent equal to BD. And by reflexive property, BC is equal to BC. Triangle ABC is congruent and equal to triangle DBC. Why is that? Well, this is our HL theorem. We have angle, side, side, or side, side, angle, But really what we have is hypotenuse, and then leg, right? Hypotenuse, leg, and we have our 90-degree angle, and that's all we need. To the proof, keep in mind that when we do a proof, whenever we're told that lines are perpendicular, we don't need to circle this and put it down below, because in order to prove that two triangles are congruent, we need to prove that sides are congruent. We need to state and prove that angles are congruent. This does neither. This is not showing us that angles or sides are each congruent. Now this will lead to angles being congruent, but this in itself does not say anything about these certain angles. So let's start with sides being congruent. Now this is saying a side is congruent, so this I can draw down. And let's mark it. Wj is going to equal to Kz. Alright, then we're told that Wz is perpendicular to Wj. Put a 90-degree box here, put a 90-degree box here. Statement 2 should read angle W is congruent equal to angle K. And what makes that true is that all right angles are congruent. On statement 3, hopefully you can tell that Jz is congruent equal to Jz, the wrapper. So Jz is congruent equal to Jz. That's reflexive. And now, note 2 in our notes, this should be angle 1 is congruent equal to angle 2. That's what we're trying to prove. And we can prove that once we prove that two triangles are congruent. These triangles are congruent, so let's go triangle JWZ is congruent equal to, and if I go JWZ, I would have to go ZKJ, and that's going to be by our HL theorem. And then last but not least, we can say angle 1 is congruent equal to angle 2. Why? Because that's by CPCTC. Our last proof. So let's take a look at what we're being shown here. First, we have AB, and I believe this sign in here, this should say, it's either going to be parallel or congruent. I think it's going to say parallel. So AB is parallel to CD. So again, let's highlight that. We always want to highlight the two lines that are parallel and extend them out, and highlight and extend out. Alright, the next thing we're told is that, also let's highlight our transversal. So that's going to be this segment right here. Alright, now as a result, because we did that, these are alternate interior angles. Let's change the color. Let's make it stand out. So these angles right here and right here are going to be each congruent. Let's put angle 1 and angle 2. These angles have to be congruent by alternate interior angles. Then we're also given that we have 90-degree angles. BD is perpendicular to AD, so put a 90-degree box here and put a 90-degree box here. Alright, with that being said, let's get to our proof. Now again, if you circle all of this and draw down your arrow, in a sense, we don't need to do that. It's not telling us anything. Remember, to prove that triangles are congruent, we need to prove congruent sides. We need to state and prove congruent angles. So we really don't need to draw the arrow down because it's not going to do anything for us. But what will do things for us is I can start off and say angle 1 is congruent equal to angle 2. And why is that? Well, those are alternate interior angles. Then we know that, let's put angle 3 and angle 4. Now, the reason why I'm not going to say angle D and angle B is there's two angles. So which angle are we referring to? So angle 3 is congruent equal to angle 4. That's by all right angles are congruent. Statement number 3 is going to read that by reflexive property, dB is congruent equal to dB. And so what that allows us to do is now we can say that we have angle side angle and angle side angle. These two triangles are each congruent. So triangle ADB is congruent equal to triangle CBD, and that's going to be by angle side angle. And then last step we can say is that AB is greater than or equal to CD, and that's going to be by CPCTC. For the algebra review, we're going to skip A. For B, our x, y point in point slope form, since x plus 1 would be -1, the y is 1. So -1, 1, rise 2, run 3, down 2 over 3. There's our graph. And then on this graph, this is in standard form. So 2x is equal to 8, x-intercept is 4, and 4y is equal to 8, y-intercept is 2, and we draw our line. Thanks for joining us. See you next time.